Hi there, this is the final lesson on numerical methods. You may remember we're trying to find solutions to equations that otherwise we can't find the answers to. So we've got equations, we've got to solve them, maybe set them equal to x, equal to the function equal to 0, and then find the answers, the x answers for it. And we talked last time about the fact that sometimes you have these weird and wonderful, well, this was called a staircase diagram, this was a cobweb diagram, where we're trying to find a solution to an equation. And these are the best options we have sometimes. We had that other method, you may remember, Newton-Raphson. But today we're looking at fixed point iteration then. I mean, last time what we were looking at particularly was what tends to happen in exams, you tend to get given this iterative formula that you then use, but there are occasions when they say, actually, we want you to find that iterative formula for yourself. And so we're going to practice that today. So I've got just one equation to start with, and there's the equation. But weirdly, we've got 5 different iterative formulae, which could be potentially the iterative formula they ask you to show that it's the right formula in the exam. So if I just do the first one, some of them are very obvious, and some of them are less obvious. And you might think, well, why would you pick one which isn't obvious? Why would you pick an obscure one like some of these down here? And the answer is because it may well be that this iterative formula, the obvious one, and the obvious one I think is probably to do what this does, and it just says move these onto the other side, so you get x to the 5 equals, what is it, 5x minus 3, and now find the fifth root of them, so x equals the fifth root of 5x minus 3, and that's it, we're done. Well, not quite done, we really should put it in the iterative formula mode, so the left hand side becomes xn plus 1, and the right hand side becomes the fifth root of 5 lots of xn minus 3, or square rooted, or fifth rooted. So that's my formula, same as over here. And as I say, this might be the perfect formula. It might be. I don't know what the equation, this equation roots are. It must have some answers, you'd think, somewhere. Might be there's an answer between 2 and 3. There might be another one between 5 and 7. Just, I mean, as I say, it's not something I've even thought about. But the weird thing is, this one might be brilliant at finding one of those roots, and might be impossible to use it to find another one of the roots. And if that's the case, then this is no good if that's the other one is the one that you want to find. So that's why we have the potential of having to do different iterative formulae for different roots. Let's go on to the second one. So exactly the same formula. This hasn't changed, so it's just designed to highlight the fact that you use the same formula. Same equation can be used can be solved using different iterative formula. So what's this one do? Now, the first thing I notice, actually, it doesn't say x to the 5, it says x to the 4. So somehow we've got to engineer an x to the 4. Now we could divide by x, but I don't think they've done that, actually. I think they've taken x out as a common factor. So I'm going to write x bracket x to the 4 minus, what's that, minus 5. And at the same time they've moved the 3 over there equals minus 3. So you can see what I've done. I've taken x out as common factor, move 3 over. And now I'm just going to divide by that bracket. So x equals minus 3 divided by x to the 4 minus 5. And you notice it's slightly different, and that's because it's got lots of minuses. So if you times top and bottom by minus 1, top and bottom by minus 1, you just change the signs, so that becomes 3 over. And you tend to write these in opposite orders when you do this. It becomes 5, minus 5 becomes 5, and x to the 4 becomes minus x to the 4, which is what they've got over here. So finally, you just write xn plus 1 equals 3 over 5 minus xn to the 4, which is what it's got, which is good. As I say, that might be the perfect one, a bit obscure, but I mean, who would think of doing that, you know? But there you go. What's the next one say? Well, the same equation, x to the 5 minus 5x plus 3. And you're welcome to pause these and see if you can do these yourselves, and then play it again when you get to the point where you think, well, I want to check it, or I haven't got a clue. But what have we got here now? One thing I notice here, it says minus 4x, and of course it said minus 5x here. So I think I need to leave 4x here, but I think I'm going to move one of those over. A bit bizarre. I'm going to move just one of x. So if I just move one of them over, I still have 4x, or minus 4x left. And I think that's it. That is it. I've just taken the 5x and I said, well, that's the equivalent of an x and 4x. I move the x onto the other side. So my final answer is xn plus 1 equals xn to the 5 minus 4xn plus 3. So that's a slightly bizarre trick, but there you go. That's what they wanted. What's the next one want? Well, I am dividing by 5 here, so I think I'm just, yeah, let's write it to start off. But I'm dividing by 5, so I think I'm going to move the 5x over, get that on its own. So equals 5x, and now divide by 5. And that equals x. Is that what they've got? Yeah, it is, and of course, I can write it like this. You know, you put the n's and the n plus 1's in. So that's good. And my last one. So again, write it out. X to the 5 minus 5x plus 3 equals 1. I'm getting bored of this now. But what was it they do in here? They've got to divide by 4. Right, well, I think it's similar to last time. I'm going to move. I'm not just moving x over. I think I'm dividing by 4, so I think I've got to put 4x over there. So if that's the case, I shall write x to the 5. Now, I've got minus 5x, so I've moved. I think I've got minus x left, plus a 3. And that, yeah, that agrees with that. Oh, look at that. That's missed out the n. There you go. Now, finally then, I've divided by the 4, yeah, so x to the 5 minus x plus 3 divide by that 4 is equal to the x. And that gives me the final iterative form, xn plus 1 equals xn to the 5 minus xn plus 3 divided by 4. So that's just highlighting the fact that iterative formulae, there are lots of different ways. And who knows which of these will find the root. Now, of course, there is a way of doing it. I might mention that again in a bit. But before I do, let's have a look at this next example, because this is, I would say, well, it's described as a tricky example, and I would definitely say that. If this came up for me, I wouldn't have a clue how to do it. If it came up in the exam, it would tell you what the iterative formula should be, and it would say, show that it is equal to this. But this goes to show, really, it highlights the fact that these are a bit weird. I've got log x minus sine x equals 0. So, weirdly, I need to write it the other way around. And I've practiced this before I did it, believe it or not. And when I didn't move it the other way around, it didn't work. So it just goes to show. So I've switched it round. I'm now going to add x to both sides. Okay, you know, you think, why would you do that? But here we go. Minus log x. So I've added it to the left. I now need to add it to the right. Equals x. I mean, it's a bit odd, this, isn't it? I mean, you'd think you'd say to yourself, well, if I was going to solve this, I'd go log x equals sine x. And then I'll go x equals, well, if I'm moving the log over, I get e to the sine x kind of thing. And you'd probably think to yourself, well, this will do as a iterative formula. Well, try it. I'm telling you now, it won't work. So, although that looks perfect, it won't work. So, we're resigned to doing this weird and wacky method over here. All right, so what's the next stage of the wacky method? Well, I'm going to times everything by x. Probably easier if I write, well, let's write x squared plus x sine x. I could have written it in a bracket, but I've decided just to multiply everything out like that. So that's everything on the left hand side has now got an x attached to it. Oh, the right hand side as well, so that becomes x squared. Now the final step is I'm going to square root everything. So if I square root everything, it becomes the square root of x squared plus x sine x minus x log x. And that is all equal to, well, I've got to square root the left hand side and the right hand side, so that just equals x. And of course this is what I'm after. I'm after a formula that says x equals. So I'm saying my iterative formula is xn plus 1 equals, well, it's the square root of xn squared plus xn sine xn. So remember to put those in brackets, xn log xn. That's amazing, isn't it? Well, I want to go through this because, I mean, I've got a few minutes left, so let me just highlight this. Now, this equation has a root down there, and just looking at it, it's about 2 on my graph. So I'm going to start off with x naught equals 2, and I'm going to chuck that into my calculator using the answer button thing that we used last time. I'm going to try and get the answer here and see if it gives me the right answer. So just turn my calculator on, make sure you're in radians. 2 equals, so that's on the screen, and then I'm going to do the square root of answer squared plus answer times sine answer, close bracket, minus answer times log answer, close bracket. And I press equals, and it gives me, oh, that's quite close. It's 2.1. Well, I don't know how many decimal places, 105. I'm going to write 3dp. I'm going to press equals again, and I've got x2 equals 2.163. So it certainly looks as if, looking at my graphs, it's found the root. It has definitely found it. So I'm going to press it loads of times so that eventually it says, all right, I've done it. So after a million goes, x, whatever that is, I'm going to say xn plus 1. Now sometimes, remember, we call this alpha for the root. But I've got 2.219 to 3dp. Now, that I think is the answer. Just looking at it, I know it's the answer. But let's assume I'd use my dodgy formula right up here. So x naught equals 2. I don't have to go through the process again. x1 equals. So, right, so 2 equals, and what did I say my formula? I said my formula was here. It was e to the sine of x of n. That was my alternative expression. So e to the sine of answer. That's right. E to the sine of answer. Comes up with very little letters in my calculator. And that's come up with a first answer of 2.48. Where's my pen gone? There it is. 2.482. Now, it's not the end of the world, 483, because it might be one of those ones that goes boom, 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 a kind of cobweb. So let's press equals again. Oh, no, maybe not. This goes x2 equals 1.845. I actually think it is a cobweb, but it's one of the ones which goes further and further away. 2.61, yeah, you can see this is diverging and not going to find me my answer. So this is diverging. This fails to find me the root. And this is what this is all about, really. Now, you may remember there were some rules. Well, these are the posh answers, by the way. That's the answers. This blue line is the weird g of x equation I've got. This is the blue line. Yeah, this is g of x. And of course, we're trying to find where it crosses the red line, and that seems to be about 2. It's an alternative way of looking at this. Let's just remind ourselves that these iterations work if the gradient isn't very steep near the root. So if the gradient is between -1 and 1 near the root, then it will converge. And if it's not, if it's, gradient of 4 or gradient of -2.7, it will diverge and it won't find the root. So that's what all this says. You need to practice this to get on top of the exercise and understand when they work, when they don't. You've already looked at this, hopefully, after the last one, exercise 14E. Have another go at the exercise, try and do some of the harder questions, and let me know if you get any problems. So all the best. Thanks.